Welcome fellow chemists to the nomenclature of the alkynes, the last of the basic naming videos. When naming the simple alkynes, apply all of the rules you know for the alkenes. What has changed is that ene is now ine, and our functional group is not a double bond, but the triple bond. Because of the similarities, check out the nomenclature of alkenes part 1 before continuing. As we saw with the alkenes, we are looking for the location of our functional group, in this case the triple bond. The first path, which is the longest possible, does not contain our triple bond. The next path, which is slightly smaller, does contain our triple bond and is 7 carbons long. The third path also contains our triple bond, but it is only 6 carbons. We pick the longest path, which means the parent hydrocarbon in this case will be heptyne. As always, the substituent is listed before the parent and numbered in the manner that gives the functional group the lowest number. With that in mind and your experience naming alkenes, why not name the molecule on the screen? So the triple bond is the ine functional group, the parent was already identified as hept, and there is also a propyl group on the molecule. With the triple bond all the way on the right, we're going to number from that direction to ensure it gets the lowest number which it can, which is 1, and the propyl group will get a 3. Now we have all the information we need in order to generate the name, and when we put it all together, we get 3, propyl, hept, 1, ine. If there are multiple substituents on the molecule, cite them alphabetically and ensure they get the lowest set of numbers you can after giving the functional group the lowest possible. As you just saw, the alkynes are named just like the alkenes, so you should have no trouble naming this molecule. So for this molecule, we have an 8-carbon parent, oct, the triple bond group is ine, and there are 3 substituents from the left in bromo, methyl, and iodo. With the triple bond itself so close to the right side of the molecule, we number from that direction, and we get 2, 4, 5, and 6 for the locations of our substituents. With the locations determined and the substituents properly identified, the name is easy to generate from here. We're going to get 6 bromo, 4 iodo, 5 methyl, oct, 2 ine. If numbering in both directions results in a tie, move to the next substituent. Whichever direction results in the lowest number now is the one to choose. This looks like a simple molecule to name, but give it a go and see how you do. The parent is 6 carbons long, or hex, and the triple bond is directly in the middle. We have the same substituent, methyl, 3 times on this molecule, so that means we are going to need to use the numerical prefix tri. Finding the locations of our 3 methyls and triple bond from the left gives us a 2 for the first methyl, a 3 for our triple bond, and a pair of 5s for the methyls on the right. However, when we switch directions and number from the right, we get a 2 for those first 2 methyls, the triple bond remains on position 3, and the final methyl is on position 5. So the numbering from the right gives us the smallest possible set of numbers. We pick these for the positions of our substituent and our triple bond functional group, and now we have everything needed to name this molecule. Putting it all together, we get 2,2, 5, trimethyl, hex, 3, ine. In a cyclic molecule, the triple bond is considered between carbons 1 and 2 automatically. Then you number clockwise or anti-clockwise to ensure the numbers for the substituents are as low as possible. Trying not to give too much away, but for the first time we do not have a 6-membered ring here, but go ahead and name the molecule. There is a 7-carbon parent ring, or cyclohept, and our functional group at the bottom of the ring, ine. The 2 substituents on the ring are both methyl, so we will need to use the numerical prefix di as well. For cyclic compounds, identifying substituents is easier than numbering. However, in the case of alkynes, like alkenes, we at least know where the position 1 must be. So starting from the triple bond and going clockwise, we get the numbers 6 and 7 for our methyls, which is, more or less, as big as it's going to get for a 7-carbon ring. When we go anti-clockwise, the numbers are 3 and 4 instead, so clearly this is going to be the direction we number the molecule. With the substituents identified and the locations appropriately numbered, we put together the name, which is 3,4-dimethyl cyclohept 1-ine. If the functional group location is the same and the next substituent is also a tie, move to a third substituent to determine the proper direction that results in the smallest numbers. This is the last of the basic nomenclature molecules, so give it your best shot. The 8-carbon parent of this molecule is oct, and our triple bond ine is in the middle. We can easily identify the 2 chlorine substituents on this molecule, so of course we will need to use the numerical prefix di, as well as the methyl group. Finding the locations of these substituents from the left, we get a 2, a 4, a 6, and unfortunately, a number we do not appreciate, a 7. When we switch sides and go from the right, however, we get the numbers 2, 3, 4, and 7. Now this we do appreciate since we get our smallest possible number when we go from the right, so we pick this set. Now all that is left for us to do is put our substituents and locations together to generate the name of the molecule, so we get 2,7-dichloro 3-methyl oct 4-ine. Due to the arrangement of atoms in and around a triple bond, alkynes do not have cis-trans or easy isomers. However, alkynes are classified based on the location of the triple bond itself. If it is at the end of the chain, it is called terminal. There is no specific notation in the name, but terminal alkynes will be numbered 1. If it is elsewhere in the chain, it will be called internal. Again, there is nothing in the name that suggests this other than the number not being a 1. To summarize basic alkyne naming, the parent hydrocarbon is the longest chain containing the triple bond. Ensure the triple bond always receives the lowest possible number. With multiple substituents, cite them alphabetically and give them the lowest numbers possible after giving the triple bond the lowest you can. When numbering from both directions results in the same location for the triple bond, make sure a substituent gets the lowest possible number. In a cyclic molecule, the triple bond is considered position 1, 2 automatically. Then number clockwise or anti-clockwise to determine the direction that gives the lowest numbers for any substituents. If the triple bond and the next substituent is a tie, move to a third substituent in order to determine the direction that gives the smallest possible set of numbers. Finally, due to the nature of the triple bond, there are no cis-trans or easy isomers, but they may be classed as terminal or internal. If all except that last rule sounded like the alkenes, you were right. The rules are very similar. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. Today's recommendations will ensure you get the quick dose of science your body needs, because if you want it delivered to you in a minute or so, I cannot recommend Minute Physics or Minute Earth anymore. Enjoy the wonderful animations and follow the stick figures as you learn everything from whether or not you should walk or run in the rain to why rivers always form curves. You will find links to their channels and websites in the description. If your body needs a refresher on organic chemistry, however, take a look at a couple of my previous videos. As always, feel free to get in touch with me via email, social media, or if you would like, make a request in the comments.